if I write more explicitly, so what is P2 UV? So the P2 UV is, shall I use UV or XY? Just use one thing actually, it doesn't matter. It's definite integrals. So P2 UV is this UV and phi 1 of UV, right? Minus R of UV and phi 2 of UV. Or should I write phi 2 first and then 1 first actually? Is it making sense? And du. Okay. R is smooth, it's a good function. So I can apply a fundamental theorem of calculus actually, think about it. So can't I write this as the integral, double integral over sigma, and then an integral which starts from, for example, phi 1 of UV up to phi 2 of UV, okay, and I have R of, really x, y, z, for example, okay, and let's call it dv. Let's call it dv. आ रही बात समझ में? या यूं कहें, जब dv ना कहें, ये कहें dx, ठीक है? You write dy dz. ऐसे ही है, एक मिनट, we should write it properly. Proper notation. No. So it should be z actually. Think about it, because the limits are on z. Okay, and you should have dx and dy. Okay.
Partial भी आएगा.
Huh?
Partial
भी आएगा. Yes, partial by partial with respect to what?
Z.
Z. अब ठीक है? So you're gonna get this. Are you getting the point? ठीक है? I don't know why, but we are getting this minus sign. Okay, are we doing one easy mistake? So the S1 is okay. Okay. So it says this. The minus is going to. Okay, even there is no difference actually, but he's putting minus 1 here actually. Okay, and 1 here. Why? Why is putting minus 1? Because he said, okay, so he says the positive direction is above direction and the negative direction is really the below direction actually. So he puts this, so you're going to have a minus here and plus here. So this would be plus and this would be plus actually. ठीक है? So what is the meta conclusion? The meta conclusion is, I took the rth component of the vector field F and integrated over the boundary of V, and this is equal to, because I can put this as, if you interpret this as the iterated integral, if you treat this as the iterated integral, you're going to have partial r by partial g integrating it over entire V and dV by Fubini theorem. Remember, this Fubini theorem can turn this iterated integral into a volume integral. Are you getting the point? So from this you got this. Can you see what would be the other arguments?
So similarly,
I'm going to say that V is Fubini type 2. You will take Q, and in that case, the way here, K dot n goes away, so here, you're going to have a vectors with the j, but the middle term will go away actually, and these two will survive. Okay, and similarly, so in other words, you can write this actually, that Q j dot n, but what would be the key thing that we're going to use here is that V is also Fubini type 2 actually. So I'm going to exploit now that being Fubini type 2 in order to, for example, solve this. And it's going to be equal to the triple integral V of partial q by partial y and dv. Okay? and similarly, what do you call for the boundary of V? And similarly, you're gonna say that you have the boundary of V and Pi, and since it's Fubini type 3, dot n, and this is going to be equal to the volume of partial P by partial x and dV. And then add 3 sides. So when you're gonna add all 3 c sides, you're gonna get the surface integral of f, okay, dotted with n over the boundary V, and this is going to be equal to, इन तीनों का सम क्या होगा? The divergence of f, you know, summed over the entire volume. ठीक है? I know that there are little technicalities, but it's not that difficult. At least you got some intuitive picture that how does this goes. So at least practice this proof, you know, at least for once properly, so that and convince yourself that why every single step is true. Don't just read it out. ठीक है, किताब वाला कह रहा है तो ठीक कह रहा होगा. Like, shouldn't be like that. ठीक है, so scrutinize it and see that why. Things the way they are.
सर Q के केस में सर हमारे S1 और S2 वाले डबल इंटीग्रल 0 नहीं हो जाएंगे?
Q के केस में.
Yes, sir.
Q के केस में the jth part is going.
S1 S2 दोनों 0 हो जाएंगे.
But okay, so here's the thing actually. Even S1 and S2 and S3 would change in case of the Q actually.
Yeah.
They will not stay same.
Oh.
Think about it. Because for Q, I'm going to say that I have one surface which is kind of making the right side of. So in other words, you tilt your cylinder actually. Okay, or you put your cylinder horizontally, and now you have 2 surfaces. Okay. So one is on the left, another is on the right, and third is this, what do you call, revolving around it actually. So this will be S1 and S2, and this third is going to be S3. Are you getting the point?
फिर से वही
So,
हो जाएगा.
huh?
फिर से फिर उस फॉर्म
So you have to do that. So S1 and S2, S3 will change actually for that. But no matter what they are, and they will exist because we have an assumption that you have a Gause region. Okay. So these surfaces are already there in your head actually.
सर अगर हम वो सिलेंडर नहीं लेते हैं उनके नॉर्मल एक ही डायरेक्शन होगा.
So don't just keep. I'm just saying that cylinder is an easy example. You can keep it in head, but it could be a complicated, you know.
सर लेकिन अगर कोई और सरफेस होगा तो उसका नॉर्मल वेरी नहीं होगा सर.
क्या मतलब?
मतलब अगर कोई कर्व टाइप सरफेस है सर तो उसका नॉर्मल जो होगा ईच पॉइंट पे वेरी करेगा ना.
But their direction is going to be opposite of the direction actually. वो जो भी vector हो.
अच्छा वो कैंसिल आउट हो जाएगा.
Yes. So their directions are going to be always the opposite of the direction. So on the top surfaces you're gonna have, you know, the normals with the one direction. On the bottom surface, no matter where they are going, doesn't matter. But they always have the opposite. So what do you call direction as the above, you know, normal vectors.
सर जब हम जो कंपोनेंट ले रहे हैं सर उसके अलावा हम सिलेंडर को सर टिल्ट कर रहे हैं सर.
टिल्ट नहीं कर रहे. हम ये कह रहे हैं हमारे पास surface एक अजीब सा surface है, in which you already have these. So think about it. So I have a Fubini type. So the real, okay, so one of the easiest example that could be, you know, all Fubini type 3 is really cube actually. Think about it. Okay, so you have these 2 sides and, you know, 3 surfaces around it, and then you have top, bottom, and surface around it, and you can think from other perspective. The sphere can also be all 3 type actually, because then you can slice it in, you know, different manners and you can get it actually.
सर कोई ऐसा एग्जांपल है जिसमें कोई भी फबीनी.
So you need to create it. So you need to have a cube. So think about a cube, but in cube you don't have, for example, planes as their side, but some surfaces, okay, as their sides actually. ठीक है? कुछ curved किस्म के surfaces हैं. You are putting them together. ठीक है? 6 की 6 sides ले लें. So take the cube, same cube, but make the every side of the cube as a curved surface actually.
सर तो वो स्फीयर नहीं बन जाएगा.
क्या मतलब? It's not going to be any sphere. It's not necessary. It's going to be something spherical.
Spherical बन जाएगा. सर
Okay.
फिर तो उसको ला सकते हैं ना फुबिनी टाइप में किसी न किसी में अगर कोई
So मैं ये कह रहा हूँ कि so take the cube, okay, and imagine that each side of the cube is flexible. You can, for example, make any kind of surface out of it actually. ठीक है? It could be something like that. That's a good one actually. That so you have it, but you do something like this. Okay. Now this is also so I can say that this is if I look at from this perspective, it's Fubini type one. So the top is S1, bottom is S2, and these two sides are representing S3 actually. Okay. But I can also look at it from look the same picture actually. But from this perspective that, okay, like now these two sides are S1 and S2, while the top and bottom is really S3. Okay? Parametric surface, joint parametric surface, okay, and so on and so forth. So it's kind of a surface in which all six sides are really, so that could be another example. So you can see that the theory, why this theory is now powerful, because it can accommodate all kind of surfaces actually. All kind of surfaces. Okay? So I'm just finishing. At least I would like to finish this chapter. I know that a little bit over time, but I would like to settle this chapter. So I have uploaded exercises too, so I will look at it as well, do the computational exercises. So the Gause regions, even, I mean, if you read it, I'm not getting into it. If you read the latter part of it, it really generalizes the Gaussian region even to more interesting kind of surfaces. For example, one example that starts with the torus actually. So torus is neither actually. Torus is neither. It's not a Gauss region actually. Okay, you can't say that it's any Fubini type. But what he's doing with the torus is that he's slicing it into the four pieces, and then you really get, what do you call these four pipe type pieces actually, and each of the pipe type region. So you so imagine in your head that you have a torus, you have this donut with you, and you are slicing it into the four pieces. So you're going to get four pieces actually, cylindrical. So you take a cylinder, but you carve it actually. So it's really a curved cylinder actually. And then each of that is really, Gauss region. And then you apply divergence theorem on each part and then sum them up and you can get. So the way you did in green theorem, think about it. So we used this green regions, green theorem, and we took it to multiply connected, what do you call, regions and Jordan regions and so on and so forth. So you can play the same with it. So you can read it for yourself. It's fun to go through that part as well. That you can even extend this theorem more to a more weirder kind of surfaces actually, which does not fall into any category. Okay. All right. So here's the thing. So imagine you have this vector field. So I'm just giving you flavor. So imagine you have this vector field which looks like 3x plus y plus z and x minus 2y plus z and x plus y minus 3z. And I have a paraboloid, an ellipsoidal. Okay, so it's like a rugby ball. Okay, think about it. So it's not an ellipse but ellipsoidal actually. खरबूजे की तरह कोई चीज है. खरबूजा कहेंगे, क्या कहेंगे, सरदा कह लेंगे or something like that. Yellow जो होता है. So it's ellipsoidal, parameterized, not parameterized, but has this rectangular equation: 4x square plus 2y square plus z square equal to 1. Okay. Z square equal to 1. And what do you want to do? You want to compute the flux of f through this surface actually. So you have ellipsoidal and you want to know that how much of f is exiting. What do we call this? So what we can do for sure is that the Gauss divergence theorem tells you that so this should be equal to so this is S, and this is really the volume enclosed by S. Okay, so having a volume that is enclosed by S, so it's equal to the del dot F and dV. Are you getting the point? Can you directly calculate this surface integral? So what you're going to need for computing this surface integral? The first thing is going to be take its projection, but its projection is going to be what kind of picture in plane? It's going to be ellipse actually. Ellipse actually. Otherwise you put v equal to 0, so then really this is really 4x square plus 2y square equal to 1 is an ellipse actually. Okay, so that would be the domain of it. What would be the parameterization of it? UV. Parameterization of it. So it's going to be UV.
So 1 minus
Yes,
square
and then compute the value of
yes, z
1 minus 4u square
plus 2v square
minus 2v square.
So in compute it's square roots.
And then square it as well. Okay, so you have this. So from where examples in the books, just read them for yourself. आसान आसान से छोटे छोटे examples हैं, ठीक है? So really the final thing that I would like to do is that consider this special vector field actually, which is say for example position vector of a point. So xi plus yj plus zk. Okay? And apply the Gauss theorem onto it. So when I'm gonna apply Gauss theorem on it, what I'm gonna get? I'm gonna get on this side, I'm gonna get on the volume side, I'm gonna get what? V is going to be the divergence of it. So divergence of it is going to be 1 plus 1 plus 1. So it's going to be 3. dV is going to be equal to the surface integral, which is going to be what? This F or maybe R dot N, okay, over the boundary of V, okay. And if you take this 3 out, then the triple integral of dV is going to be the volume of V actually. It's going to be 3 times of the volume of V, and R dot N. So here you have what you call this formula to compute the volume of the V, okay, through a surface integral.
Yes, sir.
By simply knowing the position vector, so it's going to be 1/3 of boundary of V times R dot, for example. Is it making sense? For example, you want to know that what is the volume, for example, enclosed by this ellipsoid. Okay. Then what you only need to know, just need to know in its parameterization what are x, y, z. So what is x, y, z in its parameterization actually? Okay. So R is x, y, z. So u, v and
minus x.
ठीक है 1 minus x square minus z square and that actually, ठीक है. And n कैसे compute होगा? n भी हम compute कर सकते हैं. So for computing n, you can take its rectangular equation, remember?
Yes, equal to the
ठीक है.
compute करें.
And write it in this form, 4x square plus
2y square
plus z square minus 1 equal to 0, and call this g of x, y, z. Okay? And then the n is going to be the gradient of g over the normal of.
normal.
That's it. So that would be the normal.
Yes.
And once you have all these quantities, just integrate it over x, y, z. Find your integral. Okay? So there are some examples as well of this actually.
सर ये वॉल्यूम जो हमने लिखा है इसका सर ये गिवन है सर
क्या मतलब?
कि
नहीं, that's what we need to compute at. So in other words, what this theorem is allowing you to compute the volume through just by just knowing the r and n on it and just solving this surface integral. So this is really analog to Green area formula. So that you can use the Green theorem to compute the area of a given region actually enclosed by some boundary. So now you have something like similar. Imagine you have a volume with some boundary. Okay, boundary is a parametric surface, and you want to compute its volume, so you can compute this surface integral as well. Okay. So there are examples based on it as well. वो भी आपने, for example, खुद कर दें. So these examples are important. Just go through them as well. And then there are some exercises in the book as well, in the notes as well, so go through them as well. Okay? Okay. That's it from my side for today. And that's really the end of the chapter.